Welcome to the 17th lecture of this course. Today we are going to talk about parse trees and ambiguity with respect to context-free grammars. So first let me talk about parse trees. Let me define what parse trees are and see with some examples. So for the context of this lecture, let G be a grammar, a context-free grammar, and W be a string. W be a string in the language of the grammar, let's say. Okay. So a parse tree of W with respect to G is a rooted ordered tree that represents the derivation of W with respect to G. Okay. So I haven't formally defined what we mean by derivation, and I am going to do that very soon. But basically, when we have a grammar and when we derive a string from that grammar, it happens via a sequence of substitutions. Okay. So we substitute a variable with one of its production rules, and that is how we derive a string. So a parse tree gives a parse tree gives a visual representation, or it is a visual representation of how this derivation takes place. It is a rooted ordered tree, and it gives what is called a syntactic structure of W with respect to G. Okay. So we will see this very soon. So let's look at some examples. Okay. So we will describe two grammars. So the first one, so the first example is, so let's say we have a grammar G1, which is basically the grammar for the language 0 to the power n, 1 to the power n. So G1 is described as follows. So G1 has the rules S going to 0, S 1 or epsilon. Okay. And let W be the string 0 cube 1 cube in the language of G1. Okay. So the parse tree of W with respect to G1 is the following tree. So we have a node S first, and then we have so basically the root node represents the start variable, and each level would represent what a variable in the layer just above it gets replaced with, the production rule that is used to replace the variable just above it. So S gets replaced with 0 S 1 first, then this S gets replaced again with 0 S 1, again this gets replaced with 0 S 1. So now we have a string consisting of 3 zeros and 3 ones. So this last S gets replaced with epsilon. Okay. So if I basically look at the leaves from left to right, if I concatenate the leaves of a parse tree from left to right, it will give me this string W. Okay. So, this is the parse tree for our string W. So, a couple of properties about parse trees. Okay. So, firstly, every internal node is a variable. So, internal or non-leaf nodes, so nodes which are not leaves, or in other words nodes which have some child. For example, we have this as an internal node, this and this, all of them contain variables. Every leaf node is either a terminal or it is the empty string epsilon. If it is epsilon, then it is the only child of its parent. Okay, for example, here we have leaf nodes which are symbols like 0 or 1, and there are actually other child also for the parent of any leaf node. But if you look at epsilon, the parent of epsilon, which is this node, has only one child. And then we have, if an internal node is labeled R and A1 to A2 up to AK are the children of R from left to right, then R going to A1, A2 up to AK is a rule in the grammar. Okay. For example, if I have an internal node, let us look at this internal node. So, we have some variable on it, S in this case, and if you look at the children of that internal node from left to right, 0, S1, then S going to 0, S1 is a rule in the grammar, which is what it is. Okay. And finally, concatenation of the leaves of a parse tree from left to right gives the string W. Okay, so if I concatenate the leaves 0, 0, 0, epsilon 1, 1, 1 from left to right, it gives the string W, which is 0 to the power 3, 1 to the power 3. Okay. So, one important point about this parse tree is that observe that if we take any string w that belongs to the language of G1, 0 to the power k, 1 to the power k for any k, observe that you will only get one parse tree for that string. Okay, so, there will only be one way in which 0 to the power k, 1 to the power k can be represented in a parse tree format, but this is not always the case. Okay, so, let us look at another example where this property is not true. So, let us look at the grammar for the language of all strings over 0 1 that have an equal number of zeros and an equal number of ones. So, last time we saw this example and we constructed a grammar for this language. So, the grammar was, so we have the production rule S going to 0 S 1 S, or it goes to 1 S 0 S or to epsilon. Okay, so, remember that this takes care of all strings that begin with a 0, this takes care of all strings that begin with a 1, and so on. So, now consider a string w in this language, which is, let us say 0 1 0 1 1 0. Okay, so, this string has equal number of zeros and ones, 3 in each case. So, what would be a parse tree of this? So, we can have a parse tree where I replace, okay, so we have S being replaced with 0 S 1 S, then this S is replaced with epsilon, this S is replaced with 0 S 1 S. Okay. So, and then we replace this S with epsilon, and then this S gets replaced with the production rule 1 S 0 S. We replace this with epsilon and this with epsilon. Okay. So, now if I look at the concatenation of the leaves from left to right, I have 0 epsilon 1 epsilon, sorry, 0 epsilon 1, then 0, then epsilon, then 1, and then again we have 1 epsilon 0 epsilon. Okay. So, if I concatenate them, I get the string 0 1 0 1 1 0. Okay. So, this is, let us say, first parse tree of W with respect to the grammar G2. We can also have another parse tree for W. So, I replace, first I replace S with 0 S 1 S. I replace this S with 1 S 0 S, and I replace this S with again 1 S 0 S, and now I replace these S's with epsilon, S going to epsilon, S going to epsilon, S going to epsilon, and S going to epsilon. So, once again, if I look at the concatenation of the symbols, so I get 0 1 0 1 1 0. Okay. So, this is our second parse tree for W with respect to the grammar G2. Okay. So, the moral of the story here is 2 points. So, there are 2 important takeaways. One is that whenever we talk about the parse tree of a string, it is always with respect to a fixed grammar. Okay. Parse tree of a string independent of a grammar does not make any sense, because the same string can be accepted in different manner in different grammar. So, it is always a string with respect to a grammar. That is point number 1. The second key point is that we can have grammars, particularly the grammar G2, where there are multiple parse trees for the same string. Okay. So, if you look at these 2 parse trees, the one on the left and the one on the right, they have different structure, okay, but they are the parse tree for the, they represent the same string. Okay. So, there may exist multiple parse trees for a string with respect to a grammar. Okay. An example is 0, 1, 0, 1, 1, 0 with respect to the grammar G2. Okay. What about the grammar G1, the grammar G1 that we had earlier for the language 0 to the power n, 1 to the power n? Can there be a string which has multiple parse trees? Okay. So, the answer is no, because if you look at the rules of that grammar, the production rules of that grammar, in every step of the derivation there is a unique variable. Okay. So, whenever I replace S with a production rules, I replace it with 0 S1. So, there is exactly one variable that I get in the current string. Okay. So, we do not have any choice as to which rule to apply in order to get let us say a different parse tree. Okay. In this case, that is not true, because here I have 2 variables that are there in this current string 0 s 1 s. So, either I can replace the first string of the first s, or I can replace the second s with some other production rule. Okay. So, this is what gives rise to ambiguity. So, on the other hand, G1 has a unique parse tree for every W in the language of G1. Okay. Okay. So, now let me define the concept. Now, let me formally define what a derivation is. So, the derivation of a string W with respect to a grammar G is the step by step, or maybe I should write it as is the is a sequence of substitutions that yields W. Okay. So, it is a sequence of substitutions starting from the start variable that yields W in the grammar G. So, let us look at some examples. Okay. So, again with respect to the grammar G1. Okay. So, what is the derivation of a string? Let us say if I take W equal to 0 square, 1 square. Okay. With respect to the grammar G1. So, I get a derivation. So, I start with S, then the first step is S yielding the string 0 S1. In the second step, I have S yielding this S getting replaced again by 0 S1, and then I get 0 0 1 1 where S is replaced with epsilon. Okay. So, this is a derivation, and again you can easily see that the string W with respect to the grammar G1 has only one derivation. Okay. So, you cannot have multiple derivations. But let us go to our grammar G2. Okay. So, let us look at the grammar G2 and let us try to see if we can have more than one derivations for a string. Okay. So, so this is our grammar G2, and let me take a simpler W. So, let us say I take a W 0 1 0 1. Once again this string belongs to the language of G2. So, I can have a derivation where I replace S with 0 S 1 S. Okay. Then I replace the leftmost S with epsilon. So, I get 0 1 S. Then I replace this S with again 0 S 1 S. Okay. Now, I replace the first S with the epsilon. So, I get 0 1 0 1 S, and then I replace the second S with the epsilon, and I get 0 1 0 1. Okay. So, this is one derivation. I can have another derivation of the string 0 1 0 1 as follows. So, I replace S with let us say 0 S 1 S. Okay. Now, instead of choosing to replace the first S, I replace the second S. Okay. So, I replace the second S with 0 S 1, and I replace the second S with 0 S 1 S. Okay. Now, I replace the first S with an epsilon. So, I get 0 1 0 S 1 S. Then I replace this S with an epsilon. I get 0 1 0 1 S, and finally, I get 0 1 0 1. So, note that these two derivations are not the same, but they give the same string W. I can have a third derivation, okay, where I replace S with 0 S 1 S. Then I replace this first S with the rule 0. So, I replace this S with the rule again 0 S 1 S 0 S. I replace it with 1 S 0 S, and I have the remaining 1 and S. Okay. Next, I replace the first S with epsilon. So, I get 0 1 0 S 1 S, then I get 0 1 0 1 S, and then I get 0 1 0 1. Okay. So, if I have to mark which variables get replaced in each step, here are the variables. So, first this s gets replaced with this, then I replace the first s with epsilon, then I replace this s, then I replace this s, and finally I replace this s in this derivation. In the second derivation, first I replace this, then I replace this s, then I replace this, this, and finally this. In the third derivation, I replace this, then I replace this, then I replace this, this, and finally this. Okay. Note that, so let us call this my derivation 1, this is 2, and this is 3. Okay. So, note that in my first and in my third derivation, in the current string, always the leftmost variable gets replaced. So, this is what is known as leftmost derivation. Okay. So, here also all the left, whichever is the leftmost variable in a string, that is getting replaced, and the same thing happens here. But that is not so the case with the second derivation. Here, although the first s is the leftmost s, but I am replacing another variable to get the next string. Okay. So, a leftmost derivation of w with respect to g is a derivation where in each step the leftmost variable of a string gets replaced. Okay. So, example, derivation 1 and 3 in the earlier example. So, now we say that a string w belonging to L of g is ambiguous if it has two leftmost derivations. Okay. So, we say that a string is ambiguous if it has two leftmost derivation. You can see that this string is an ambiguous string with respect to this grammar. We say a grammar G is ambiguous if there exist some ambiguous string in the language of G. So, our grammar G2 is an ambiguous grammar, whereas our grammar G1, if you remember, so that is an unambiguous grammar. If you can check that every string will have a unique leftmost derivation. And finally, we say that a context free language L is inherently ambiguous if all CFGs accepting L are ambiguous. Okay. So, if we have a language for which every grammar is ambiguous, then we say that the corresponding language is inherently ambiguous. Okay. So, I will end here with a note that so this is one way of defining ambiguity. Okay. So, an equivalent way is that we say that a language or a string is ambiguous with respect to a grammar if and only if it has more than one parse tree. Okay. So, one way of defining is with respect to derivation. If a string has more than one leftmost derivation, we say it is ambiguous. Also, if it has more than one parse tree, we say that it is ambiguous, and both these notions are actually equivalent. One can actually prove that. Okay. So, thank you.